All right, folks, let's start. Okay. Hello, everyone. This is Dr. Yuzo. This is ECE 360 control system class. And today is our 16th lecture. Okay, 16th lecture. And first of all, to your most concern, the midterm 2 is still under grading. So we are expecting to see the review and the results, everything by Wednesday. Okay. On Wednesday lecture, we will do everything about the midterm 2. According to the grading so far, it seems good. Most of you guys are having correct procedure at least, and but on Wednesday we will talk about more details. Okay. All right, today is the first lecture for our new module, module 6. Root locus. Okay, we are right here at this cell. Well, of course, can you guys hear me well? All right, good. Then we go on here. So we are at this cell, and Monday of week 9. Okay, Monday, week 9. And obviously, we have passed half of the semester, more than half, actually. And we will have 3 lectures, including today's, to finish the module 6, the root locus. And followed by the module 7, which is a design using the root locus. So this module 6 is more of conceptual problems. Okay, so you want to learn what is going on and why it is so, and or say the bottom line is, no, what is it? What is it? What is it for? Okay, because during the past years, I found this is a very hard to understand concept. You want to pay enough attention on the concept. Now, what is it, and how you form a root locus? Okay, because it's not something very straightforward. So today's lecture very important, very important. And module 7, as I said, gonna design, and which also gonna assign the project by the end of the module 7. Okay. So if you understand the module 6 well, it's very helpful for you to conduct the design project for module 7. Okay. All right, let's get it started. So module 6, the root locus. Let's first of all answer some questions. Okay. First question is, what is it? And here I'm using RL to represent root locus. Okay, so just be aware of this. And just like what? The similar things, we also have what? What is it? Closed loop transfer function, right? Closed loop transfer function. So these kind of abbreviation I'm used to use. What is a root locus? And then we will answer. Second question is, what is it for? Okay. And then third question, a basic question, or say, is how to obtain or say sketch a root locus. Right. Obviously, this is based on given what? Transfer function. So these are the questions we're gonna answer for today. First question. And let's number them. 1, 2, 3. So question 1. What is it? What is it? The definition is like this: graphic representation of closed loop transfer function, pause as in k varies from 0 to infinity. This is a kind of definition. It is graphic representation, of course, is corresponding to the name locus, right? Or say loci as plural. Okay? Singular is locus. What is it? Is a locus of closed loop transfer function poles. It's not any other type of transfer function, but closed loop transfer function. And here we can recall what we learned before, include closed loop transfer function, include open loop transfer function, include forward transfer function, right? We used the forward transfer function for what? Anyone still remember? Forward transfer function. For what? For midterm 2, right? At least you should answer in this way, right? Specifically, what forward transfer function is for us to find what? Anyone still remember?
Steady state error.
Steady state error. Very good. Okay, 2 was right. Steady state error. Okay, Jeff knows that too. Okay. Steady state error. We used forward transfer function. Therefore, if anyone in the exam try to even or just even to find a closed loop transfer function, then well, quite a bit of point can be lost. Okay. Forward transfer function, and also we have a feedback transfer function. Right? At least we learned up to 4 different kinds of transfer function for a given system, right?
If there is no feedback in general, can we assume that the error is just 0?
There's no feedback.
Yeah.
And
So
the
there's
system
no error.
is an open loop system like this, right?
Yeah.
Then your error is, well, I doubt anyone going to study the steady state error for such kind of system, because such kind of system, well, except this is a closed loop transfer function, which actually including the feedback inside, you're not seeing it. However, the total transfer function is closed loop transfer function. It's represented by a single transfer function, which include, again, many details inside. That's possible. However, we cannot study the steady state error for a given closed loop transfer function. That doesn't make any sense. Okay, without seeing the inside details, we can't do anything about the steady state error. Except we directly observe the output, which is C. And then you know your reference, right? The difference between them is the steady state error. You can tell that. Does it make some sense? So yeah. Steady state error is what? Steady state error is always the difference between input reference, or say reference, okay, and the output. In other words, input reference is whatever you want the system to output. However, the real output might deviate from your whatever you wish by some value, right? That value is nothing but error, the steady state error, okay, at steady state.
So you could almost say that RS minus CS would be the steady state error for a closed loop transfer function?
Yes, you can do that. You can.
Okay.
Yep. All right, going back to this Locus once again. Okay, remember this very firmly. Okay. This is something you can never forget. It's a locus, or say a pause, of closed loop transfer function poles. However, if given a particular specific system, you can only have limited number of closed loop poles. Therefore, if you place them into a graph, what do you see? Bunch of dots. Does it make sense? Rather than paths. It won't be a locus. Does it make some sense? Even your transfer function, you place all of the poles, no matter how many, into a graph. What do you see? Bunch of dots, nothing more, right? However, how you form this locus, how you form a path. Here's how. You're introducing a gain k. You're introducing a gain k, and also making the k vary. The k varies from 0 to infinity, like this. Okay, for example, let's assume you have a transfer function, generic transfer function, or say block diagram like this, right? And then from here, you know the closed loop transfer function is obviously g over 1 plus g times h. Right? This is what we learned from module 2, I think. Right? And then from here, you know you can find the closed loop transfer function poles, who are also the roots of denominator. Okay. And they might be as 1, 2, 3, limited number of poles. Right? And if you just plot them, what do you see? Plot poles into S-plane. What do you mean by S-plane? S-plane means this. Okay. S-plane means you have very simple. It's just that you have a real axis and you have an imaginary axis. Because poles here, generally speaking, is what, complex number, right? Of course, it might be a real number. However, it's which considered as one special type of complex number. Does it make sense? So all of these poles are complex numbers, and then you can place them into an S-plane like this, right? Real part versus the imaginary part. So no matter how many you have, there are a limited number of what points, right? Here, maybe here, here, maybe here, here, here. They're points, nothing more than that. Okay. Of course, here, remember how to plot them. Actually, your closed loop poles labeled as this, as a cross, okay, in the S-plane. So once again, given a specific system, you have a particular closed loop transfer function, and then therefore you have a limited number of poles. You're placing them into S-plane, and they just shown as what? Bunch of dots, bunch of crosses, per se. It won't be path until you are introducing a k here. What does it mean? You're introducing k here, which is the gain of the total transfer function of the closed loop transfer function. Introducing a k here, and also you vary the k, okay, from 0 to infinity. Now, actually, how we introduce k is introduces k here. Introduce k here along the forward path. Introduce k in forward path. Therefore, the resultant closed loop transfer function is what? K times g over 1 plus what? kgh, right? Denominator is becoming 1 plus kgh. rather than 1 plus GH. Therefore, you can imagine if we are varying K value here, your denominator polynomial is changing. Does it make sense? Your denominator polynomial is changing, then you're going to have what? Different closed loop poles. Which means you K vary from 0 to infinity. Your closed loop poles, these dots gonna what? They're gonna move, right? They're becoming different values, which have different different real part and different imaginary part. Therefore, they can move. Basically, they're moving, right? Does it make sense? You're changing K value, okay. Their poles are changing too. If the K change continuously, if K change continuously, what happened? So do the closed poles, right? So do the closed poles. Therefore, what we're gonna see, instead of seeing bunch of cross or dots, you're seeing path. Does it make sense? And since your change of K is from 0 towards infinity rather than from infinity to 0, that means what? K has a direction, right? It's one way changing. Therefore, so do the what? Rule locus in red. They're changing what? Towards certain direction, one way. Right? So rule locus has direction because the change of K has direction. So this is how you are seeing paths, because you're introducing a new gain K here along the forward path, making your denominator of the closed loop transfer function different. So if you change the K value continuously, then so does the closed loop transfer function denominator, polynomial. So your closed loop pole is going to change continuously as well. They change continuously, then they are nothing but what? Path, not dots anymore. This is how we end up with a rule locus. Form process. This is nothing but rule locus. Does it make some sense? Is it too bad? Not yet, right? Any questions, concerns? All right, so this is the answer for the first question. What is rule locus? Okay. This is what rule locus is. Okay. And second question, what is rule locus for? Rule locus can do for us. Obviously, it can help us to design the controller, which is the subject for next module. Analyze the control systems. And basically, it means this. For example, you have only a plant. You have plant They might have feedback already. What you're gonna do is design a controller to improve the system. Make it becomes like this, right? Right. So obviously here we need to understand what are we going to improve. Yeah, what are we going to improve, or say our targets, or our target. Improve what? Three things, right? Basically. First thing is called stability. Second is what? We know this very well. Third is so-called transient. So obviously these two are something we have learned a little bit from previous module. Recalling we have output C of t, right? For a second order system, typically we have such kind of output. And from here, you can tell the steady state value, right? The steady state value. And also before reaching the steady state value, before reaching and stay in the steady state value, you have what? Say this is settling time. Before settling time, this is what? We call it transient, right? We call it transient. And here from the settling time on, then we call it steady state. Right? So this is steady state value. This is the settling time. And before the settling time, between 0 and settling time moment, we have transient. We call it transient. After that is steady state. So these two are pretty much talking about this output, okay, how to make your output as a perfect steady state, which means what? Which means your steady state error is 0, right? And this means you are reaching and staying whatever I want you to output. Perfect. And also you need to take care of the transient. Transient means here how you reach that value. How much overshoot, remember? How much rising time, how much settling time you spend. Right? All of these matter for those transient. Okay? So steady state error. Transient means TS, overshoot, TR, etc. These are the things we have been talking about. Okay? We have been talking about. Only thing left is the stability. Okay? Stability. The stability concept and how to judge we will talk about in this module. Okay. And also never forget we have what? Design what? We're already descending, right? In other words, who is the most important thing you need to worry about? Stability. If the system is not even stable, it's meaningless to study the steady state error or transient. You don't even talk about them, wasting your time. But once the system is stable, and then next you need to study if the steady state error is small enough, right? The smaller the better, remember? The smaller the better. 0 is perfect. If it is 0. If the steady state value is not perfect yet, don't waste your time to go ahead for a transient. That's meaningless. So this is a priority. There's a priority. It's descending. Who is the most important thing? And then followed by next. And then the last one is transient. Okay. So this is very important. Okay. And of course, what does it mean by stability? Stability means if the output, which is C of t, can reach and stay a steady state at a steady state. We will see some more examples to say this. We had a little bit discussion before about the stability, but we will see more details in this module. This is what the rule locus can do for us: design, analyze the control system. We will see how to do it. Of course, this is module 7. Okay. More details we will see from module 7. Okay. The last question we need to answer. Going back to here. Last question here is how to sketch a rule locus, okay, based on the given transfer function. You have two ways to sketch the rule locus. First one is hand sketching. We have a handout I have posted in the Canvas. What matters is just how to use it. Right? Handout is a handout. I mean, it's part of your cheat sheet. Okay, you don't need to memorize anything. You just need to understand how to use it. How to use it. If you see that. A second way is obviously what? MATLAB, right? How to use MATLAB to program. I have also posted this MATLAB learning material in the module 6 in Canvas 2. All right. Okay. And specifically, we are using a script file to program. Well, the MATLAB Simulink can do the same thing, can do the job as well. Okay, don't forget that. But in this particular course, we are learning how to program everything by script file programming. Okay. Simulink is something, in my opinion, is relatively easier stuff. We probably won't need to teach too much. But what we need to remember here is what, no matter which way, okay, no matter which way, we're using what we are using is open loop transfer function to plot the rule locus. And the rule locus is the path, or say the locus, of the closed loop transfer function poles. This concept and this description is very confusing. I admit it. However, by learning more, it makes more sense. Okay, now you just need to keep your notes or mind, which is even better. We're using we're using open loop transfer function to plot the closed loop transfer function poles as the rule locus of the system. Open loop transfer function to plot. Okay. All right, if this is fine, then let's go ahead to see some details. Let's see some details. Let's first of all finally learn the accurate definition for the stability. Given the system, what does it mean by stable? What does it mean by unstable? You have actually up to 3 scenarios. Okay, 3 scenarios. First is obviously stable. Second is called marginally stable. The last one is unstable. 3 scenarios. So let's visualize a output to see what scenario, what does the output look like if it is stable, marginally stable or unstable, right? First of all, let's have a look. Stable is very obviously, you might have a transient which might be long, might be short, depending on the transient. But no matter what, eventually you reach and stay at a steady state value. Flat line here. That's what I mean. Stable. And when you describe this phenomenon, what do you say? Say is reaching and stay and staying at a steady state. And more importantly, you should say the transient. How about transient performance? What? The transient oscillation decay. To 0. There's no oscillation anymore. Decays to 0. Once again, it takes different amount of time. Okay, it might be very long for you to reach that steady state. It might take a very short time. However, the transient oscillation eventually always decays to 0. This is steady, stable. A stable system output looks like. Okay. Then what is the marginal stable? Well, we can skip the second case for a moment to take a look at the third unstable system output look like first, right? What does it look like? What happened? We can easily call it disaster, right? But how to describe it? How to describe it? So it never reached a steady state, and the transient. What happened? Growth, right? It's growth. It's not decaying. It's growth. Growing. It's unstable. It's you want to avoid such scenario at all cost, right? Like we just said, is the first priority concern. Stability. If it is unstable, then it's meaningless to study anything else. The third case, the marginally stable. Marginally stable means what? I think it's very easy to guess, right? It's not, the transient is not going to decay to 0, but it won't grow either. What does it mean? Stay the same, right? Or say the constant magnitude oscillation. This is how they look. This is how they look. But more importantly, how you link such system output performance to the system transfer function. This is something more important. And this is something more important. Because most of the time, we are not going to be able to see the output, right? I mean, if given the output, you can directly tell. That's very easy. However, before seeing output like this happen, you want to know that by studying the system transfer function. Does it make sense? You can't wait until the disaster like this already happened to know it is unstable. That's too bad. Too late. So how can you tell which is which? Okay, here is how can you tell. My notebook page is not wide enough, so I have to start from the second line here, but I'm still using 3 parallel lines to indicating the stable, marginally stable, and unstable, okay? So here we go. Okay. Still 3 parallel lines, you know, what are they respectively? So first, to stable case, what do we have? Closed loop transfer function, poles are only located in the left half plane. And the margin stable, what do we have? And is closed loop poles are in left plane and on the imaginary axis. Unstable means what? Unstable means any closed loop transfer function poles are in the right plane. Well, by the way, what does it mean by plane? Plane means nothing but the S-plane here, the real part versus the imaginary part. Very straightforward. just means this plane in where we're going to plot our rule locus on. This is a so-called plane. So if given the rule locus, you can tell these two, right? You can tell all of these things too. And if just given the transfer function, or say closed loop transfer function, how can you tell which is which? So first case, for a stable system, the closed loop transfer function poles are only located in the left half plane. What does it mean is what? It means what? Closed loop poles, because closed loop poles are a bunch of, once again, complex numbers, right? These number what? Real part, what? Less than 0. Does it make sense? All of them, okay. All of them. All of those closed loop poles, real part less than 0. Or say all of the closed loop transfer function denominator polynomial roots have a negative real part, meaning the same. Right? Now, how about this? The second case, marginal stable means what? Means closed loop poles, real part, either in the left top plane or on the imaginary part. So how about this? Less equal. Here is a little bit tricky, okay? Be very careful. Here is saying and. So maybe more accurate here is should be like because less or equal, this symbol means, because this symbol means what? Either or, right? But this is not either or, right? Okay, it's and. Does it make sense what I'm talking about here? To be marginally stable, you must have something along the imaginary axis. Okay? You must have something there. If without anything along the imaginary axis, that is what? Stable. So it's not either or, but and. Does this logic make sense? So this simple, no, not quite accurate. I don't like this. I label them as the less than 0, which means left half plane and on the imaginary axis. Any questions? Does it make sense? Anything? Any feedback? If not, we can move on to the next case. Unstable. Unstable means what? Unstable means how? What is it? Means any. Any means what? Any means as long as you do have. Okay, as it means, it might be 1, it might be 2, it might be more, but as long as you do have it. Any closed loop poles, real part is what? Greater than 0, right? Very good. I'm seeing here Alex is doing very good job as a TA. He's answering a good question with a good answer. Perfect. You have multiple poles. Okay, it's not single pole, it's multiple poles. Okay. Some of them might be on the left, some of them on the imaginary axis, and some of them might be on the right. Okay. Yep, perfect. Thank you for both of you. Okay. Good. And further, since this is a good concern, I think let's just take a look at example. Given closed loop poles location. What does it mean by closed loop poles location? That means in this graph, we are seeing bunch of crosses. So pretty much you're labeling all of the closed loop poles into the S-plane. Okay, that is called locations. First example is like this. Okay, take a look at this. Second system, if you locate all of the closed loop poles into the S-plane, you're seeing this. Three different scenarios. Well, first of all, you need to be able to tell they are three different scenarios. Yep, this example obviously gonna also answer the question from Elliot. Okay, let's see. First case here, this guy. After locating all of these poles into the graph here, which case it belongs to? Stable, marginal stable, or unstable? Which case? Margin, here we go. Kevin is right. First one, then marginal stable. Take a look at the second one, and then we go back to see why. Okay. Second one, here. What is it?
That's unstable.
Unstable. Good. Good. There we go. Unstable. Good. Last one. What is it? Stable, right? Stable. Yep. So from here, I think we can tell how we better understand these three things, right? These three things. The first one, the white is marginally stable. Well, we are seeing three poles on left half plane, and once again, and you're seeing what? Some poles on the imaginary axis. Right? This is what? Marginally stable. Here we go. Here we go. Second case. You have some on the left, some on the imaginary axis. In the second case, you're seeing what? You have some on the left, but you have one on the right. What is it? Unstable. That's why we call it any. I don't know, or say we don't care how about the rest of the closed loop poles. As long as you have one or more poles located in the right half plane, that is unstable. Okay, so as long as you have, then it's unstable. Period. Okay, that's why it's called any. It's a very strong, very solid requirement. And then how to make the system really stable? Nothing along the imaginary axis, and then of course, let alone the right half plane, right? So all of the poles, all of them, every single one of them has to be located in the left half plane. that system is stable. Therefore, what can we do? What can we do is pretty much, so can tell stability by finding, once again, closed loop transfer function. Okay, here must be closed loop transfer function poles. Can tell stability by finding the closed loop transfer function poles. Because obviously we can't wait until seeing the disaster happen to know it is unstable system, right? We can't do that. That's terrible. We have to be able to predict. We have to be able to tell before that, before seeing the output happen. And how? Closed loop transfer function poles can tell that. And this example, pretty much 3 examples here, trying to help you visualize what do they look like. What do they look like? All right, we can say a little bit, just a little bit more. Okay, so the first, the marginal stable case. If you have a pole here, what is it? Immediately unstable, right? You have something along the y-axis, you have something left half plane, but all of those become meaningless since you have one, and even if just only one in the right half plane, right? Immediately unstable. So we are not talking about how many on the left, how many on the right. We are not talking about that. We are talking about as long as you have something on the right, unstable. This is a firm or solid and stable. And here, stable system. Think of one question, okay? If this pole, instead of here, this pole is moving towards right a little bit to here, but not reaching the y-axis yet, then what's the difference between here and here to this system? Anyone have a conclusion?
Mathematically, you're reducing the real part, the negative real part. It's becoming less and less negative, or as large of a negative.
Therefore,
I mean, slowly you reach to marginally stable and then eventually unstable. If you kept adding.
Yes, but that's what matters. So by this moving from the black to this red, the system becomes less stable. Does it make sense? The stability is worsened. Does it make sense? And this is very important. However, on the other hand, what else is happening? Now, Kevin got a good point too. Kevin's saying maybe the amount of the transit time increases or decreases, right? So from black to red, the real part is decreasing. If you only talk about the settling time, which is, if you recall, the formula is 4 over the magnitude of real part, what happened? Increases. This is what Kevin means, and a very good point. So moving the poles here can introduce 2 things. One is stability change. Another thing is the transient going to change too, right? And this is how we actually going to conduct the design in next module, right? How we locate the pole location to a proper location so that we can have decent transient and good enough stability. Yep, Alex got that too. Okay. Very good, very good, very good, very good. So once again, keep in mind, moving the location, we are going to change the stability as well as the transient. And more details we will see. Okay, you will see more details for sure. But here, just the concepts. Today is about concepts. Good. Very good. Any other questions before we move on? All right. We talked about system stability. Okay. And next, let's try to understand the rule locus a little bit more. First, let's have two specific systems. First, the systems we have second system. Let's study the rule locus. To system one, since we just mentioned the to plot the rule locus, we need open loop, right? Open loop transfer function. Therefore, the open loop transfer function for system one is what? Forward transfer function times a feedback transfer function, right? Which is 1. Remember? This is definition for the open loop transfer function. Very important. Okay, very important. And then the rule locus of system 2. We also need to find the open loop transfer function. So system 2 is what? What's the difference between two open loop transfer function? Nothing but the gain, right? Nothing but the gain in the numerator. One is 1, the other is 10. The tricky thing is here. The further, if we plot the closed loop transfer function post pass, which is rule locus, we're going to introduce gain here. In other words, introduce gain here, and then resulted gain here, in k here. Okay? This is what we're going to do. And varied k, of course, there from 0 to infinity. The conclusion is both have exactly same look root locus. First of all, does this make sense? Or say why they have exactly same look root locus? Why is that?
Well, because the poles are staying exactly the same. The only difference is just a constant. So, I mean, we could just multiply system 1 by 10, and that's the exact same thing. And since we're sweeping k, we're increasing it from 0 to infinity. Eventually, these two are going to converge to the same thing, right?
They're basically right. So if we try to plot it, let's try to plot them. Okay. No, we are not trying to plot it. We are trying to see it. Okay, how to plot it? We are not there yet. Okay, we are not there yet. So say this is system 1, right? This is system 1. This is system 2. Let's see how they are same. Okay, so we locating the poles. We don't need to know how to plot them. Let me just present the rule locus. Okay, system 1 rule locus looks like this. Okay, looks like this. Maybe we learn how to plot them next lecture, I believe, but now let's try to understand them better. Once again, they have exactly the same look, okay? Exactly the same look. The trick thing is, if we locate one particular point, for example, let's talk about just these particular point here, which correspond to point here. I know my sketching is not perfectly matching each other, but what I mean is we are selecting the exactly same location, same point. They all correspond to one particular K value. Does this make sense? This point is not, I'm not talking about rating, okay? Because these are poles location. I'm talking about they correspond to certain K value, right? Making that pole location happen, right? So if this K is 150, it's making this location happen, then what is K value for system 2? What do you think? Same location. Very good. 15, right? 15. Does it make sense? Basically, just like this. This guy equals to 150. This guy equals to what? 15. Right. Reaching the same location, okay. However, your K value different. Does it make some sense? Sure, no problem. Good. So you're stretching, extending your locus, your path by same amount, same level. However, you're using different amount of K value because of the different gain K here.
So why is it in between pole 0 and pole -1?
Mm-hmm.
Like
no, the how to sketch the rule locus in red color here and here we will discuss in the next lecture. It's not what we're discussing now.
But you have a line between pole -1 and 0, or is it?
Yes, you have rule locus between 0 and 91, but you don't have any rule locus between 91 and 92. No.
Okay, so yeah. you drew a line between -1 and 0 then.
Yes. Okay. Yes. There's rule locus here and here. They're called the rule locus along the real axis, and then maybe you see how we do that. But here is kind of the concept, just the concept. Once again, my sketching is not perfect, but what I mean is choosing the exactly same location rule locus. Because they look exactly same. However, at same points, they have different K value. Different K value, right? And now let's take a look at the one more thing. Impact on the transit. Let's see example here. Once again, repeating what we have had the conclusion. So moving closed loop poles, location, of course, we are talking about. In the S-plane, stability, and the transit will change accordingly. And this is the conclusion we have drawn. And then see a specific example. Right? Assuming a second order system, the rule locus is given as below. Now, if increase, say this is, if increasing k from K1 to K2, how transient including TS, TP, and overshoot will change. And also, what's the K, or say, what's the range of K value for a stable system? I see these two. All right, let's see the solution here. All right, first, look at 2 points we are selecting along the rule locus. First point corresponding to one particular K value, we call it K1. Second point is up here, corresponding to a different K value, we call it K2, right? So first, saying increasing K value from K1 to K2. This is pretty much telling you K1 is less than K2, right? First of all, why is K1 less than K2? Anyone can tell? Of course, the problem is telling you that, but why K1 is less than K2? Why is that? Anyone knows? Anyone? Come on, speak out. Speak up. But Kevin's answer is fraction, which I don't follow. Sawyer's answer is definition of RL. And any more details? The definition of RL. Which part of definition is telling you K1 is less than K2? How do we explain this?
Because root locus, it's the graphic representation of the pole's path as K goes from 0 to infinity.
So
0 has to increase incrementally.
he is right. He is right. So basically is what? Look at the direction, or say the direction of the root locus, okay? What does it mean? When K is equal 0. Basically starting point, right? If you consider this as starting point, is moving towards K equals to infinity, right? So obviously this point happens before this point, right? So this one has smaller K value. That's why. Yes, the definition of root locus, that's correct. Okay. Why? Because this is pretty much the moving with the increase of K value. That's why K1 is less than K2. Okay. And here, pretty much comparing these 2 points, two closed loop poles location corresponding to different transient performance. So how about TS? From here, move to here. How TS change? Anyone knows? And of course, here we need to recall what? The formula for these 3 guys, right? First of all, TS equals to 4 over magnitude of real part. TP equals to what? I over magnitude of imaginary part of the pole. Right? Overshoot is a little bit tricky. It's the exponential negative real over imaginary I. Right? So if these 3 formula, and then we think about this. So from 1 to 2, TS is decreasing or increasing? TS. This is not difficult, right? TS, TP, not difficult. I think overshoots is a little bit. TS is what? Decrease. Good. How about TP? How about TP? There we go. Decrease. Good. Good. Both TS, TP decrease. Good. Good. Right. Why is that? Well, because of this, right? You're from here, move to here. Both real part and the imaginary part are magnitude. I mean, magnitude, okay. Magnitude are increasing, right? Both magnitudes are increasing. Therefore, both TS and TP decreasing. Good. Right. And last one, overshoot. Anyone has any conclusion here?
I would almost think that we would have to take the slope to figure out when it's all of a sudden.
Exactly. Exactly. So the conclusion is what?
At first, I would think, is it increasing and then decreasing, or eventually when it obviously K increases and goes farther and farther?
Decreasing and increasing? No. There's no such. There's no back and forth. No. There's no back and forth. How is it? Is it increasing? Is it increasing? Why is it increasing? Like John mentioned, we need to measure the slope, kind of slope. What does it mean? He means this. Let me use a ruler. So first point is pretty much is here, right? The slope is here. Second point, the slope is here, right? You see now I have these two lines. You can tell the different slope between the first point and second point. By the way, why is a slope? Slope means what? Slope means imaginary part magnitude over what? Real part magnitude. So from point 1 to point 2, what happened of this guy? What happened? Decreasing, right? Does it make sense? From 1 to 2, your imaginary part is increasing, while your real part is what? Increasing as well. That's why you only need to check the slope. Right? Imaginary part over real part. Does it make sense? That's right. It's imaginary part is imaginary part is growing slower than the real part, making the ratio in between decreasing. Does it make sense? I'm sorry. Oh, the other way. The other way. I'm sorry. The imaginary part, yes, Kevin was right. Okay, Kevin was right. The imaginary part is growing faster than the real part growing. That's why the ratio in between is growing. Right? This introducing what? Because here, this guy is what? Decreasing. Because here, be careful, it's a real part over imaginary part. Okay, so it's not imaginary part over real part. Therefore, this guy, this ratio is decreasing because it's backwards. It's reciprocal to that. Okay. Therefore, the entire function is increasing. Entire exponential function is increasing. Yes, the magnitude of the real part, magnitude of the imaginary part growing faster than the magnitude, than the growing of the magnitude of the real part. Okay. That's why making this ratio increasing. Okay, so the index here is decreasing, and the entire exponential function is increasing. Okay. Does it make sense? Because from here you can also tell this. So from this slope to this slope, the slope is increasing. All right, if this makes sense, then next, what's the range of K to make this system stable? Any questions? Good, very good. Yeah, Kevin is right. As long as K is greater than 0. In other words, any K value can make this system stable. Any K value. Why is that? Once again, your beginning is K equals 0, okay? And your rule Locus is moving towards the left half plane all the way to infinity. There's no chance for the rule Locus go back towards right to pass the y-axis. No chance. So it doesn't matter k value, as long as it is growing from 0 to infinity, then the system is always stable, because look at your poles. The path of poles always fall into the left-hand side of the plane. Okay? There's no chance for the rule locus reach the right half plane. Good. All right, I think that's all for today's lecture. Right, so you guys want to review this part to understand the rule locus better, since obviously the module 6 is mainly about the concept. I won't be surprised that many multiple choice questions happened in later exams. All right. Thank you for attending today's lecture, and see you all on Wednesday. And yes, we will review the midterm 2 on Wednesday. Okay? All right. Thank you. Bye-bye.